Hi everyone, in today's lesson we're going to be looking at how to apply the binomial theorem to expand polynomials. So first of all, we're doing a little warm-up here. The first one, a plus b to the 0. Anything to the 0 power is 1. All right, except for 0. 0 to the 0 power is undefined. But if we said we have a to the 0, that would be equal to 1. If we have b to the 0, that would be equal to 1. So we have a plus b to the 0 power, that equals 1. And then for the next one, we have a plus b to the first. Well, anything to the first power is itself. So we have a plus b. And then we have a plus b squared. And if we FOIL that, we're going to get a squared plus 2ab plus b squared. All right, now the next one, a plus b cubed, as you know, that's going to take us a little bit more time. We're either going to use our column method or checkerboard, and we're going to expand that. So let's do that down below here. So we know that this means a plus b times a plus b times a plus b. So we have a plus b times a squared plus 2ab plus b squared. And we're going to distribute a to every term and b to every term. I'm going to use my column method to do that. So when I multiply a by every term in the trinomial, I'm going to get a cubed plus 2a squared b plus ab squared. And when I multiply b by every term in the trinomial, I'm going to write those aligning with like terms in this first expression. So b times a squared, I'm going to get a squared b. Then b times 2ab, I'm going to get plus 2ab squared. And b times b squared is b cubed. All right, I'm going to add those together. And I'm going to get a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, that was a lot of work. And the whole point of this lesson is to eliminate all of that work, to understand what patterns are, and then use those patterns to help us expand polynomials that are raised to a power in a much more simplified process. So let's just put this up here. We've got a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, just so we can identify some of these patterns, I'm going to put an a or a b with every term, just so we can identify how the exponents behave. So I'm not going to change anything. I'm going to put, with this a here, I'm going to put b to the 0 power, because anything to the 0 power, right, is just 1. So I haven't changed anything. And here I'm going to put a to the 0 power. And again, I haven't changed the term. I'm just putting an a and a b so that every term has both of those. So let's see, we have a squared, b to the 0. This is a 1 and a 1. And here we would have a to the 0. Here we would have b to the 0. And here we would have a to the 0. Okay, so let's take a look at the exponents. So this is to the first power. So a starts at 1 and goes to 0. B starts at 0 and goes to 1. We have a plus b squared. So a starts at 2, goes down to 0. B starts at 0, goes up to 2. This one's to the third power. A starts at 3, goes down to 0. B starts at 0, goes up to 3. So we see a pattern with the exponents, right? Now, we're also going to take a look at the coefficients, and we'll do a little bit more in depth on the next page. I just want to highlight all the coefficients. We've got 1 and 1, right? And if we were to just take those coefficients out and write them out, just the coefficients, you would begin to start to see a pattern with that, all right? And first of all, you recognize we have all 1s down the side. right? And then if you really examine this for a while, you would realize that if you draw a little v like this, 1 plus 1 gives me 2. 1 plus 2 gives me 3. 2 plus 1 gives me 3. So the numbers that are happening inside are actually forming a pattern by adding the two numbers above. All right, so let's go to our next page here. Now, if you really want to see something a little bit more detailed, I have a video called Binomial Expansions Using Pascal's Triangle. That's about 5 minutes or so, and that will really break down those patterns again if I went a little too fast in this video. And if you're raising a single binomial to a power, this is called expanding the binomial. And so we looked at that in our warm-up, right? A plus b squared gave us this, a plus b cubed gave us this, and we started to look at the coefficients. Pascal's triangle provides an aid to expanding the binomials. Pascal's triangle is a triangular array of numbers formed by first lining the borders with ones, as we examined, and then placing the sum of the two adjacent numbers within a row between and underneath the two original numbers. All right, so we started that on the page before. We don't even really need to expand a plus b cubed now to understand that we know there's going to be ones on the ends. And then we know that we're going to add these two numbers to get to the next row. There's ones on the ends. And we're going to add these numbers to get to the next row. And what we've created now is what's called Pascal's triangle. So that'll help us be able to expand polynomials in a much simpler, faster method. And we're all about being, quicker and efficient. So let's take a look at the next page. Right, so this diagram that I have at the top sort of, is just a summary of what we just talked about, just to have it there as a reference. And notice that when we're picking the row of Pascal's triangle that we want, we're going to be adding 1 to whatever our exponent is. So let's say we're looking at, let me explain that. Let's say we're looking at a plus b squared. We're going to be looking at the third row of Pascal's triangle. If we're looking at a plus b to the fourth, well, this is the 2, 3, 4, fifth row of Pascal's triangle. So just be aware of that, because Pascal's triangle, remember, starts at a plus b to the 0 power. So you have to add 1 to whatever your exponent is to determine what row you want to choose from the triangle. All right, so we're looking at x plus 1 to the fourth. Now, if we were going to do this the traditional way, this would take us quite a bit of time, but we're going to do this really quickly using our knowledge of patterns and Pascal's triangle. Okay, so this is x plus 1 to the fourth, which means we're going to be using the fifth row of exponents for Pascal's triangle. So we know our exponents are going to be all highlighted in yellow here, 1, 4, 6, 4, and 1. So we're going to write those out first. 1, 4, 6, 4, and 1. And we know that we're going to be applying exponents to x and to 1. So I'm just going to write those out here, x and 1, 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 plus between. All right, now we also had studied what happens with the exponents since we are at the fourth power. We're going to start at 4 with our first term and go down to 0. And then on the second part of this term, we're going to start at 0 and we're going to go up to 4. So we're done. We've already expanded it. We're just going to clean it up and make it look a little nicer. We don't really need to write, for example, to the first power anywhere. And we really don't need to write the terms that are to the 0 power because anything to the 0 power is 1. So let's just write this out a little neater. The first term is just x to the fourth. And we have plus 4x cubed plus 6x squared plus 4x plus 1. Done. And hopefully you have found that that is much easier and we are much happier doing that binomial expansion than having to use a column method or a checkerboard or, tediously expanding that out. All right, let's try another one. This guy is to the 5th power, which means we're going to use the 6th row of Pascal's triangle. So we have, our first row, our second row, our third row, our fourth row, our 5th row. We need our 6th row of Pascal's triangle. So our coefficients are going to be 1, 5, 10, 10, 5, and 1. Let's write those out first. And then we have x and 2, so we'll write those. And just notice that I'm using parentheses. Parentheses around these will help when we apply exponents, especially when we involve negative values. It's just a good habit. We'll put plus between all of them for now. And now we'll apply our exponent. Well, we know that we start to the 5th power. So the first part of each term, the x's will start at 5 and go down to 0. And the 2 part of the term will start at 0 and go up to 5. And another thing to notice here is that since we're to the 5th power, we have 6 terms. 1, 2, 3, 4, 5, 6. This guy was to the 4th power. We had 5 terms. Just another thing to notice to make sure you're doing it correctly. Now we're already done. We did the expansion. All we have to do is clean it up because remember we're saying that anything to the 0 power is 1, so we don't need to write those. And we don't need to write to the 1st power. We're just going to clean this all up and make it look a little neater. So for the first term, we just have x to the 5th. Now for the second term, what we have is we have 5 times 2 because we have this 2 to the 1st. So we have 5 times 2, so we're going to get 10 x to the 4th. For the next one, we have 2 squared, that's 4, and 4 times 10, that gives us 40. The next term, we have 2 to the 3rd, that's 8. 8 times 10, that gives us 80. Then we have 2 to the 4th. 2 to the 4th times 5 is 80. And 2 to the 5th power on the last term is 32. Okay, and we're done with number 2. So much easier. I hope you're enjoying this. Okay, now we're going to just step it up a little because we have a minus 2 here. And again, that's why I've been using parentheses all along. It's a good habit, especially when we have part of the term is going to be negative. Right, so this is x minus 2 to the 3rd power, which means that we're going to use the 4th row of Pascal's triangle. So this is the 1st row, the 2nd row, the 3rd row, the 4th row. Our coefficients are going to be 1, 3, 3, and 1. Let's write those. 1, 3, 3, and 1. And we're going to fill in our x and our minus 2 for every term. And this is raised to the 3rd power, so we're going to start at 3 for the x part of the term and go down to 0. And for negative 2, we're going to start at 0 and go up to 3. Now we just have to be careful when we simplify this because we do have negatives involved. Well, the first term is just going to be x to the 3rd because anything to the 0 power, that part of the term is going to be 1. So we have x to the 3rd. Negative 2 to the 1st power in the 2nd term is just negative 2. Negative 2 times 3, that's going to be negative 6. So we're going to have negative 6 x squared. Then we have negative 2 squared, that's positive 4. 4 times 3 is 12. So that's 12x. And then the last term, we have negative 2 cubed, that's negative 8, times 1, we end up with just negative 8. And that one is done as well. And notice that when we did have that negative part, that another pattern you'll see is positive, negative, positive, negative. It'll alternate signs between terms. Okay, let's keep going. So that was Pascal's triangle, and now we're going to take a look at the binomial theorem. The binomial theorem eliminates the use of drawing out Pascal's triangle because what we find out is that you can use combinations to help us do the binomial expansion. And just so you know, a combination in mathematics is the selection of R objects from a set of N objects where order doesn't matter. And if you arrange the values of N combination R in a triangular pattern, you will also get Pascal's triangle. So now we're saying we're taking this all one step further, and we're saying that we don't even need to remember Pascal's triangle or write it all out. We can just use N combination R. And here we go. We have the official binomial theorem, which I'm sure looks very intimidating, but we're going to break it down. Before we start, we have to make sure that you know how to put combinations in your calculator. So this is demonstrated in these pictures here, but I'm going to go to the calculator now. And for example, we're going to do 4 combination 0. So you're going to press the number 4, you're going to go to math, and you're going to go over to probability. And you'll see that number 3 is NCR. That's the one we want to choose. And we're going to do 4 combination 0. Okay, so we need to know that. If we didn't remember Pascal's triangle, the first coefficient in our expansion would be 4 combination 0, if we're raised to the 4th power. The second one we could also use something where we repeat the command. You may or may not have seen this before. We would do second enter, and that'll just repeat the command for you. And then we're going to see what the next coefficient would be if we're raised to the 4th power. It would be 4. If we want to see the next one, second enter, change this to a 2. It would be 6. Second enter. What's the next coefficient going to be? And then second enter. The last one should be 1. Remember, we always begin and end with 1s. All right, so let's go back to our notes. You're probably feeling a little confused, but I'm going to make it all okay with our first example. So we're going to use the binomial theorem. We're going to forget all about Pascal's triangle. I know you're thinking, oh, well, I feel really good about Pascal's triangle. I don't want to forget about it, but I'm just going to show you how we can make this now even easier without even writing out Pascal's triangle. We're going to use those combinations. So our coefficients, and we know that our coefficients are going to be 1, 4, 6, 4, and 1. We just did it in the calculator. And we know that the 5th row of Pascal's triangle uses those. But if we didn't remember that, we would just note what the combinations are. So it would be 4 combination 0. Okay, then it would be 4 combination 1, 4 combination 2, 4 combination 3, and 4 combination 4. And we would put those in our calculator, which we just did, and we would note that this is just 1, this is just 4, this is just 6, this is 4, and this is 1. And now we're going to just proceed like we did in the past. We're going to write our x and our 2. So we have x and 2. And we know since we're to the 4th power, We're going to start at 4 and go down to 0. We're going to start at 0 for 2 and go up to 4. And we're going to simplify and we'll be done. The first term is just x to the 4th. In the second term, we have 2 times 4, so we're going to have 8. 8x cubed. In the third term, we have 2 squared, which is 4, times 6. That gives us 24. X squared. Then we have 2 cubed times 4. That's going to give us 32x. And then we have 2 to the 4th. And 2 to the 4th is just 16 times 1 times 1. So our last term is 16. All right, let's try another one. Use the binomial theorem to expand x minus 2 cubed. All right, so we know that we are going to start with 3 combination 0, then 3 combination 1, 3 combination 2, 3 combination 3. And we would go to our calculator and we would enter those in. 3 combination, choose number 3, 0. We know it's going to be 1. We begin and end with 1. Second enter. So our coefficients are 1, 3, 3, and 1. So we're just going to fill that in right here. 1, 3, 3, and 1. We'll start with x and negative 2. We'll write those all in. And since this is to the third power, we're going to start at 3 for the x and work down to 0. And for the negative 2, we start at 0 and we go up to 3. Almost done. We're going to simplify this. We have x cubed. Anything to the 0 power, what we're noting is just 1. For the next term, we have negative 2 times 3, so that gives me a negative 6. For the next term, we have negative 2 squared times 3. Negative 2 squared is 4 times 3 is 12. And then for the last term, we have negative 2 cubed is negative 8 times 1 times 1. So the last term is negative 8. Okay, for number 6, I would suggest you pause, try it, and when you're ready, come back and watch the video. Right, we have x plus 5 to the 5th. We have to use the binomial theorem, so we're going to write out all of our combinations first. And because it's to the 5th power, we know we're going to have 6 terms. All right, so we're going to write it all out. Now, we always know in Pascal's triangle, because of our knowledge of Pascal's triangle, we don't need to waste time putting this in the calculator or this in the calculator. We know those are 1. We just want to, figure out what is 5 combination 1 through 5 combination 4. I'm going to go to 5, I'm going to go to math. I'm going to pick number 3. You can just press number 3. We want to know what's 5 combination 1. We're going to do second enter to repeat the command. What's 5 combination 2? Second enter to repeat the command. Second enter. So the remaining coefficients that we need are 5, 10, 10, and 5. Now we're going to fill in our x and our 5. Since this is to the 5th power, we're going to start our x's at 5 and go down to 0. And the part 5 in our terms, we're going to start at 0 and go up to 5. Pluses between. Simplify. So the first term is x to the 5th. The next term we have 5 times 5, so that's going to be 25 x to the 4th. Next term is 5 squared times 10, 25 times 10, that's 250. The next term we have 5 cubed times 10, that's going to give us 1250. And we have 5 to the 4th times 5, that's going to give us 3125. The last term we have 5 to the 5th power, that's going to give us 3125. Okay, that's all I have for this video. I hope that you've got a really good understanding of Pascal's triangle and how to use the binomial theorem. And from this day forward, you can use the binomial theorem to just make your life a whole lot simpler whenever you're expanding these binomials. All right, everyone, have a great day.